So we can get right to work reviewing these problems. So let's take a look. So this first set of problems, this is a redo from the previous homework set where we had a little trouble with this the first time. So I wanted to reinforce these. So let's take a look.
Okay.
So it looks like in the first example, you said that the reactions were unreasonable.
Yeah.
Why were the first set of arrows unreasonable?
Because the sodium ion causes there to be a negative charge on the oxygen next to it. And that's where the chain of the arrows should begin.
That's right. So we always want, we usually want to use the atoms with the charges. So this was one that we got incorrect previously because previously we had said these were reasonable, but they're really unreasonable because it's better to use the oxygen with the negative charge than to use the neutral oxygen. And I think you then put in some reasonable arrows that ended on the oxygen with the positive charge. Okay, good. It would have been tempting here to have the oxygen with the negative charge directly attack the oxygen with the positive charge.
Mm-hmm.
But that actually wouldn't work because that would break the octet rule for that oxygen. So you found a better set of arrows here. Okay. The next set of arrows, it looks like you said, were unreasonable for a similar reason because they weren't using the oxygen with a negative charge. So you fixed that. The third set of arrows looks like you decided were reasonable, and they are. They're ending up pointing towards the carbon with the positive charge. Okay, good. Let's move on. Next set of arrows looks like you said was reasonable. It's pointing to the oxygen with the positive charge. That's right. Now that arrow does not break the octet rule. That arrow now does not break the octet rule because remember you can only break the octet rule if you're forming a new bond to an atom. But that arrow is only forming a lone pair. Okay. Then the next set of arrows you decided was unreasonable. Why was that second set of arrows unreasonable?
Well, it looked like it was going to be forming a new bond with sulfur and breaking the octet rule.
Right, that's right. It was forming a new bond with the sulfur without breaking a bond. So that would have broken the octet rule. So you fixed that. Good. Then your next set of arrows you said was unreasonable. Now this next set of arrows with the nitrogens, that doesn't break the octet rule because the nitrogen is both gaining and forming a bond. So why did you reject those arrows?
The positive charge originally was in the middle chain of arrows rather than in.
Yeah, we've memorized that we want charges to be at the beginning and the end of the arrows, not in the middle. Why is it bad to have the charge in the middle? It's bad to have the charge in the middle because then the charge can't change.
Yeah.
With your new set of arrows, would the charge change?
It would.
That's why that new set of arrows is better. That's going to get rid of the positive charge. Very good. The next set of arrows you said was reasonable, and they are. Good. So let's move on. Next set of arrows, it looks like you said were unreasonable, maybe because they were breaking the octet rule again. Now, then you put in your own arrow here. So let's see. Your arrow is... Okay, good. So that arrow that you drew in there was quite reasonable. It's taking electrons away from the negative aluminum and pulling them towards the positive chlorine. It doesn't break the octet rule because it's forming a lone pair, not a bond. So that's good. Now, it turns out there's other arrows that are also reasonable there. So there's more than one set of arrows that are reasonable. That's one set of reasonable arrows, and there's others you could have drawn as well. But what you drew was reasonable. Good. Second example, you said was unreasonable. Again, the positive charge was in the middle. So you changed the arrows so the positive charge was at the end. Okay, that was good. So let's move on. Next set of arrows you said was reasonable. Good. Now, I think before, earlier, I think the first time you might have said that these arrows were unreasonable because they were creating charges. You had said last time that these arrows were unreasonable because they're creating charges, but we saw that that's not really a rule. It's almost inevitable if everything starts neutral that you're going to create some charges. Since everything here started neutral, there's almost nothing you can do without creating charges. So these are reasonable. The arrow does not begin on a negative or end on a positive, but that's okay because there were no negative or positive formal charges. Now, why is this not breaking the octet rule, since the aluminum is gaining a bond without losing a bond?
Isn't aluminum an exception with the octet rule that it can actually hold another pair of electrons or another bond?
That's right. Why?
Okay.
That's right. How do you know? So you might have a little bit forgotten that, but you were on the right track. The idea is neutral metals and semimetals have incomplete octets. Neutral metals and semimetals have incomplete octets, which means they have room for more electrons. So the aluminum here is a neutral metal towards the left of the periodic table, so it actually started with an incomplete octet. That's hard to see because we didn't draw all the bonds in the lone pairs. But if you had drawn them in, you would have seen the aluminum starts with an incomplete octet. So anyway. So you are on the right track there. That's right. So it does have room for more electrons. Good.
Okay.
Then the next example was reasonable. Why does that not break the octet rule? The carbon is gaining a bond without losing a bond.
Carbocation has an incomplete octet.
That's right. Do all cations have incomplete octets?
No.
No, only carbocations.
Yeah.
So for example, that's why the third example was incorrect, because an oxygen with a positive charge starts with a complete octet. So that arrow was breaking the octet rule. So it looks like you fixed it. Okay, these rules are actually pretty complicated now that we go through them, so you can see why a lot of students never really quite learned them, but I think we're making good progress on this. All right, so the next rule the next one was also breaking the octet rule again, and then again you fix the arrows so that it doesn't break the octet rule. Okay, let's scroll down.
Looks like the same issue there. The oxygen already had a complete octet.
One moment. Yes, you're correct. That's the correct analysis. Very good. Okay, so let's move on. Okay. Looks like you said that was unreasonable, presumably because it was pointing away from the positive charge. So you changed it so it would be pointing towards the positive charge. Let's see.
Yeah.
Okay. This one's tricky. The arrows that you drew, the arrows that you drew are consistent with the rules we've seen so far. Eventually we'll see that they're really not the best arrows. Those arrows you drew are not the best arrows, but they're consistent with the rules we talked about so far. So that was a fair work there. Okay, and as we go on, we'll see how to draw better arrows. But what you did, you drew good arrows based on what we've talked about so far. The next one, looks like you said was unreasonable. Again, it's breaking the octet rule. So you fixed it so it doesn't break the octet rule. Good. And the third example was breaking the doublet rule. So you fixed it so it's not breaking the doublet rule. The next example was breaking the doublet rule. So you fixed it so it's not breaking the doublet rule. All right, good. Next example you said were acceptable, and they are acceptable. Good. Next example looks like you said was acceptable, and it is. Next example was breaking the doublet rule, so you fixed it so it doesn't break the doublet rule. Next example is acceptable. Good. Next example, you scroll down a bit, was breaking the doublet rule, so you fixed it so it's not breaking the doublet rule. So you came up with an interesting set. You came up with a pretty complicated set of arrows there, but those arrows you came up with are possible arrows. So that was good on that example. Okay, so that finishes that review. So we redid those because the first time around we weren't quite getting them all right, or getting them all right for the best reasons. But now I think we're making some progress on that. So let's look at this next set. All right, so to determine whether these are arrow. All right. So looks like you decided that these arrows are reasonable, and they are. You numbered everything. That's good. Let's see. This is kind of complicated example. Let's see what we got here. 4, 5, 6. So 7 ends up attached to 1.
Yeah, that's right.
And then that's 2 oxygen. Good use of numbers. You changed 2 charges. How did you know the new form would form between the new bond would form between 1 and 7 instead of 2 and 7, since the tail is between 1 and 2?
Well, 2 is receiving electrons from an oxygen bond, a pi bond there, so it had to lose a bond.
In order to not accumulate charge. Good, we've talked about that. That's something that you might be able to do kind of automatically now without even overthinking it. Very good. All right, so this was review of what we went over earlier, drawing the product based on the arrows, and you're still executing that well. That's good. This is we should be satisfied with this because, again, this is a reaction that you've probably never seen before. It doesn't matter whether you've seen it or not. It's a real reaction from the second semester. Once you've seen the arrows, you can draw the product. You don't need to have this memorized. Okay, excellent. That was good. So let's move on. All right, these problems are similar to the ones we were talking about a moment ago. Let's see. The first set of arrows was unreasonable because it wasn't using the atom with the negative charge. So you fixed it. Now that's, hopefully that seems obvious to you now, but students very often get that wrong. Very often students that draw arrows here would not use the oxygen with the negative charge, probably because it wasn't drawn with a negative charge, right? That oxygen wasn't drawn with a negative charge. You had to draw the negative charge in by realizing it was an ionic bond. So that's the key to that. Good. The next problem was breaking the octet rule. And you came up with a way to not break the octet rule. Good. The next example, what's wrong with the example on the middle, the third example?
The charge was in the middle of the chain of arrows.
That's right. We've seen that we can automatically eliminate something where the charge is in the middle, and you fixed that. Good. Let's keep going. Next example, again, the charge was in the middle, so you fixed it. Next example, this example does not break the octet rule because the aluminum is a metal. And we saw that metals, neutral metals and semi-metals have incomplete octets. Good.
Yeah.
Third example was breaking the octet rule, so you fixed it. Now this next example was, again, breaking the octet rule. So you came up with a way to fix it. This is a type of reaction that you hadn't seen before in the first semester, but you might remember of seeing some other similar examples in other problems. So you drew a similar pattern here. So you did come up with a way. By turning it into a cycle of arrows, you made sure that everybody that was gaining electrons was also losing electrons. Now, we haven't talked about how to determine when a cycle of arrows is reasonable or not, but anyway, this does match the patterns we've seen before. It doesn't break the octet rule. Okay, good. So let's move down. The next example was, again, breaking the octet rule. So you changed that by changing it into a cycle of arrows, so it doesn't break the octet rule. Or did you? Let's see. What did you do here?
That arrow I could have drawn a little bit better. It should have been coming from the bond rather than the atom.
That's a good point. I hadn't thought about it. I was going too quickly here. That's right. I missed that. So your first arrow was incorrect. That's good that you fixed it because the tail has to come from the bond there, not from because there are no lone pairs. Number your atoms. It's okay you didn't number the atoms here already because we weren't drawing the product, but now we'll number the atoms. All right. Why was the first set of arrows, why was the black arrow bad?
Well, because looks like I didn't quite fix the problem.
Right.
Carbon 2 was receiving electrons without losing them, and it looks like I perpetuated that same problem.
That's right. You didn't quite fix it. That's good. So let's try again.
I think that
a new set of colors. Good. All right. All right. That will work much better. Yes. So your previous set of arrows, I guess the purple arrows, don't work because your second arrow was not taking electrons away from 2. It was taking them away from 3. And 2 was the one that was breaking the octet rule. It was tricky to draw the arrows here because you and I haven't gone over all the rules here. But anyway, let's see. Now you have a new set of arrows.
I think that should work.
Okay. Yeah. Now, so these new set of arrows do not break the octet rule. They don't turn out to be actually what happens, but they don't break they don't break the octet rule. So they would be possible arrows. The arrow that you had a moment ago was also correct, though. I'm not quite sure why you changed it. You had one set of arrows, and then maybe let's actually go back. You can maybe hit undo.
Sure. I think what I had was it was going up here.
Yeah. Why did you erase that? Any particular reason?
It looked weird to have an arrow head and tail both coming from that bond between 3 and 4. But is that okay?
A head. Who's the tail that's coming from there? Isn't that that's a different set of arrows, though?
Oh, you know what? Okay, yeah, I see, yeah. I see it better now. I was thinking there needed to be one more arrow, but there does not need to be.
So you actually kind of have a cycle of arrows now.
Yeah.
And that cycle of arrows makes sure no one's going to break the octet rule. All right, we won't worry about this too much because this is a set of reactions you haven't covered yet. The important thing was that the black arrow was breaking the octet rule, so we know that was not right. The black arrow was breaking the octet rule, so we know that wasn't correct. And the first set of arrows that I think you had drawn originally to fix that hadn't really fixed it yet because you hadn't actually removed a bond for carbon 2. Okay, fair enough. It's good that you saw this as breaking the octet rule, so let's keep going. These arrows are reasonable. The carbon in the middle is both gaining a bond and losing a bond, so it doesn't break the octet rule. The next set of arrows are reasonable. The next set of arrows. What was wrong with the third set of arrows?
Well, I thought it would be better to have the leaving group be the positively charged nitrogen rather than the chlorine.
Okay, I can see that. That's fair thinking. One thing you might not have remembered, though, is remember we said that the rule is you always want, when possible, to put a negative charge at the beginning of the string of arrows and a positive charge at the end of the string of arrows. But we did say that there were some exceptions to that, and one exception we mentioned is that usually when there's 2 formal charges in the same molecule, you won't use both of them, if you remember that. We haven't talked about that too much. But usually when there's 2 formal charges in the same molecule, you're usually not going to use both of them. Actually, there's exceptions to that as well. That's not a hard and fast rule. But in this case, then, we should not automatically have rejected the black arrows because there was 2 formal charges in the same molecule. All right, okay. But it's good that you're focusing on the charges, and it's good that you're trying to use the charges. That's a pretty subtle issue, and we haven't talked about that much. The first set of arrows actually are pretty reasonable. You shouldn't be surprised if you don't use both charges when they're both in the same molecule. That actually happens somewhat frequently. On the other hand, your new set of arrows are pretty reasonable too. Your new set of arrows are pretty reasonable too, but this is a good opportunity to remind ourselves that when there's 2 formal charges in the same molecule, we often do not end up using both of them. Okay. So the first set of arrows was okay, but your new set of arrows is also reasonable. There's more than one thing that could happen here. The last set of arrows was already reasonable. Good. So the key thing to do is not just to star that question, but maybe make another note on your paper. Remind yourself of that rule. When there's 2 formal charges in the same molecule, oftentimes we don't end up using both of them.
Okay.
Like I said, this is pretty challenging. There's quite a few rules. There's quite a few rules, and we just have to keep going over them as to get more and more comfortable with them. All right, let's see. Did you answer question 3? Okay, good. Nucleophile, electrophile, leaving group. Nucleophile donates electrons to join an electrophile. Electrophile receives electrons to join a nucleophile. Leaving group receives electrons to leave something. Good. So those have to be completely and utterly memorized. It looks like we have them down for now. Good. When an atom has a negative formal charge, what role is it likely to play?
I think I forgot to write that, but it would be the nucleophile.
Why?
Because it donates electrons to join an electrophile.
And a negative charge would make you want to donate electrons to get rid of its charge.
Exactly,
okay.
Yeah.
Okay, so overall that was good work. So I gave you, that was a lot of problems. That was a lot of problems. But we need a lot of problems because, like I say, this is challenging material, and we need to really internalize all of those rules so that they come to us automatically, and we don't need to think about them very much. So it's good that you took the time. It's good that you took the time to do all of those questions, and I think we had a pretty high accuracy rate. We got almost all of those correct. So that shows some good progress there. Okay, good. So let's move back to my screen. Let's see. Okay, so can you identify an atom here that will play a particular role?
Yeah, the bromine, because of the formal charge it has being negative, will likely be the nucleophile.
You know it's negative because of the ionic bond, so would this go at the head or the tail of an electron-pushing arrow?
Tail.
Now, I'm just going to say that so far we don't know who's going to go at the head, although maybe you do know, but we haven't talked about any rules yet that would tell us who would be the electrophile here. Like I said, this is an important habit. It's important in organic chemistry to be able to draw just half of an arrow. If you only know where one part of the arrow goes, just draw where one part of the arrow goes. You don't need to know where all the heads and tails go before you start drawing stuff. Okay, so we can say this would be the nucleophile. Who's the most reactive atom here?
The most reactive? Perhaps oxygen.
What I was going for is the bromine because it's charged.
Okay, yeah, I see.
Because it's charged. So the point is, what do you do when you're trying to predict what will happen in a reaction? Well, start by focusing on the most reactive atoms. And who are the most reactive atoms? Usually the ones with the charges. That just comes back to the thing that we've talked about many times. What's the most important factor in organic chemistry? The charges. Okay?
Yeah.
That should be obvious, but it's amazing how often students just ignore that idea. Okay? Let's see. Okay. Predict what role an atom would play here.
Well, it looks similar to the previous equation. The bromine, because of its negative charge, would likely be the nucleophile.
Does it go at a head or a tail?
The tail.
And you know, in this case, I think we can pretty much guess where the head should go.
Yeah, right on that carbocation.
Is that going to break the octet rule?
Not at all.
Because carbocations have incomplete octets. So what role does it seem like carbon-2 is playing?
The electrophile.
That's right. We haven't really talked about that rule yet, but it should be pretty obvious anyway that this would be the electrophile. Good. And what role was the bromine playing?
The nucleophile.
Good. Okay, can you identify a role that an atom would play here?
Well, it looks like carbon number 2, because it has that negative charge, would be a good nucleophile.
So should it go at a head or a tail?
The tail of an arrow.
And we haven't really gone over the rules yet to determine who would be the electrophile, so I'll just leave that blank so far. Okay, this might not seem too impressive, but this is good. This is a nucleophile you've never seen before. This is a nucleophile that's introduced in the second semester. If you've never seen this before, how could you possibly predict it would be a nucleophile? Because we've learned the general rules. Even though you've never learned about this type of molecule before, this is called an enolate. You haven't studied enolates yet. Even though you haven't learned about enolates, you can predict what it's going to do by focusing on the most important factor in organic chemistry, which is the charges. Okay, very good. Let's see. Okay, so what we've been going over here is a rule. What role would you expect this atom to play?
Nucleophile.
Sadly, we've seen that almost all rules in organic chemistry have exceptions. So now we'll have to go over the exception. The rule was pretty simple. Okay, what's the charge on this sodium?
Positive.
So this looks like an ionic bond. Who has the negative charge? That might not be 100% obvious, but it's not the hydrogens that get the negative charge. It's the boron here that gets the negative charge. Notice this is boron, not bromine.
Okay.
Okay, now let's try to predict what's going to happen in this reaction. So who's the most reactive atom here?
Well, it looks like boron would be.
Yeah, it's got the negative charge. We don't use the sodium. That's a spectator ion. So you might expect that we would do something like this. This doesn't make sense, though, because this would mean that the electrons were coming from a lone pair. But this boron doesn't have any lone pairs. That's not obvious. That's not obvious, but you actually, in a way, it kind of is obvious, because how many bonds does the boron have?
4.
4. And how many electrons then are in the bonds?
8.
So that's already a complete octet. So it can't have any lone pairs. So so this arrow doesn't really make sense, because it would seem like this is taking electrons from a lone pair, and the boron doesn't have any lone pairs. So instead, in this case, we'd have to put the tail on the bond. Okay, now here's a tricky question then. Who's going to be the nucleophilic atom here? And this problem, let's not use the rule we were just talking about. Let's try to use the rules we talked about in our previous sessions to figure out how to interpret this arrow. In fact, maybe I'll show you the rest of the arrow here. This part isn't obvious, but I'll just tell you.
Okay. Well, the nucleophile would...
Who's going to end up bound to carbon 2?
Hydrogen.
Now, that's right. Why did you say the hydrogen will end up bound to 2 and not the boron? The tail is between the boron and the hydrogen, so how can you tell whether the boron will form the bond with 2 or the hydrogen?
Well, the boron already has a full octet, so it would need to form a new bond. Well, I guess... What would happen to hydrogen? If it were boron? It's a good question. I'm not quite sure.
Okay. Now, this looks like something we should review then. This is an issue that we actually talked about previously, but we might have forgotten a little bit how to apply this. So remember, the issue here is that we have a tail between 2 atoms. And if you remember, we've talked about this quite a bit. When the tail is on a bond between 2 atoms, those types of arrows can seem ambiguous, but usually there's ways to figure out the correct way to interpret those. And I think we might have forgotten the trick for this type of arrow. So the key thing is, if we draw the arrow so we want to get rid of this negative charge, right?
Right.
Well, how can we get rid of the negative charge? By attaching the boron to carbon 2 or by attaching the hydrogen to carbon 2?
The hydrogen.
Because now what's going to be the charge on the boron?
Neutral.
That's success, right? Because we got rid of that charge.
Right.
All right, so that's the explanation. It's better to think that the hydrogen will attach to 2 rather than the boron to get rid of the negative charge. If we did it the other way, if we attached the boron to carbon 2, what would be the charge on the boron in this picture?
Well, it would be a negative.
Its charge wouldn't change because it would just be shifting its electrons. And what would be the charge on the hydrogen?
The hydrogen would have a positive charge.
Because it lost the electrons. So my point is this is the incorrect approach. And how can you see it's incorrect? Because not only does it not get rid of this charge, it actually makes a new charge. We want to eliminate charges. So this arrow is much better. This interpretation is much better because it eliminates the negative charge on the boron, whereas this interpretation would not eliminate the negative charge on the boron and would create a whole new charge on the hydrogen. You were kind of reaching towards that when you said what would happen to the hydrogen, but we hadn't quite spelled it out. Okay, this is actually an issue that we talked about in some previous sessions. We talked about how to try to interpret arrows when the tail is on a bond. They might seem ambiguous, but there's usually a way to figure out the best way to interpret that type of arrow. Okay, so who ended up being the nucleophile here? So remember, this is the incorrect arrows. Perhaps I should just erase this then, so we don't get confused about that.
It looks like hydrogen would be the nucleophile because it donated bonds to join.
The key thing is it's the one that joined carbon too.
Yeah.
Remember, a nucleophile joins something else. Well, it's the hydrogen that's joining something else. Now, do you see why I would say this might seem surprising? Do you see a naive student, I think here would assume the boron would be the nucleophile because it has a negative charge.
Sure.
However, as I was saying, now we're going over an exception to our general rule.
Okay.
So would you agree this is kind of the pattern of the exception? And in this case, it was the atom attached to the atom with the negative charge that ended up being the nucleophile. Now, how do you know when this exception applies? How do you know when to use the rule and when to use the exception? Well, the key thing is this applies when the atom with the negative charge is a metal or a semi-metal. We've already seen that those have some other differences from non-metals. If you can you find boron in your periodic table?
Yeah.
Notice that it's above aluminum, I believe. So boron is classified as a semi-metal. It's towards the left. Okay, so here's our exception to the rule. When the negative charge is on a metal or a semi-metal, it's the attached atom that's the nucleophile. Also, where is Z going to get the electrons from that it's donating?
It's going to be getting them from the bond between the metal or semi-metal.
That's something else that's new, right? Because normally, I didn't actually draw this. So normally nucleophiles get their electrons from where?
A lone pair?
Yeah, normally nucleophiles get electrons from lone pairs. But in this case, it's coming from the bond. After all, these hydrogens don't have any lone pairs. Okay, so those are a couple of new ideas here. Okay, so here's the rule and the exception. So can you predict here what's a role that one of the atoms is going to play?
One of the hydrogens would be the nucleophile because aluminum is a metal or a semi-metal.
With a negative charge. Good.
With a negative
And where
charge.
would the hydrogen get the electrons from that it's donating?
The covalent bond between hydrogen and aluminum.
So we'd have to rewrite this to draw that.
Yeah.
And so far we haven't gone over the rule for who the electrophile should be. So what would be the common mistake? I think most students would just do this, put the tail on the negative charge. But we've seen that doesn't work when the negative charge is on a metal or a semi-metal. Let me make this a little bit more straightforward. The metals or semi-metals that you will see in OChem are boron, aluminum, and iron. You may as well make a list of those. I don't think you're likely to see too many other metals or semi-metals. You can kind of memorize these. So these are the elements where this exception applies. Boron, aluminum, and iron.
So silicon is not one of those?
Silicon is a metal, but it's not a metal that's used in organic chemistry.
Oh, okay.
So my point is, obviously these are not the only metals. You know, there's dozens of metals. There's many, many metals. I'm only listing the ones, though, that appear in organic chemistry. And actually, I'm sure there are reactions that involve silicon in organic chemistry, but they don't come up much in an introductory course. So we're just covering, these are the elements that you're likely to see in your introductory course.
Okay.
So let's try to predict a role that an atom would play here.
One of the chlorines would be a nucleophile.
And where would it get its electrons from?
The covalent bond from the negatively charged iron.
So notice we have to draw in a new bond. Oftentimes we have to draw new stuff in. So again, the common mistake would be to do this. It's natural to suppose the iron is going to be the nucleophile, but that's not going to be the case here. If you think about it, notice we're not just memorizing this exception, we actually explained why this is an exception. We explained that this would not be a good arrow because, well, in this case, we didn't quite explain it. All right, we haven't explained every single little detail. We've kind of memorized this pattern. But in any case, we know that if the tail is between these two atoms, it's better for the chlorine to be the nucleophile so the iron can lose its negative charge. So we've at least partially explained the pattern. Okay, but also we should just memorize this so that we don't need to think it through on every problem. We want to also have these rules basically memorized. Good. What's a role that an atom would play here?
Looks like carbon-4 would be a nucleophile.
And where does it get its electrons from?
A lone pair.
So this is just our rule. This is just the normal rule because the carbon is not a metal or a semi-metal. So this is just the normal rule we talked about before. Okay?
Yeah. Okay, all right, so we've talked about that. That has to be memorized so that we don't forget it, but I think we have that down for now. So let's keep moving forward. Let's see. So who should be the nucleophile here? The iodine. It has a negative charge.
So does it go into head or a tail?
Tail.
So now let's move forward and try to figure out who's going to be, what's the name of something that reacts with a nucleophile?
An electrophile.
So who's going to be the electrophile? Well, we might start by asking whether this would work. Can we treat the oxygen as the electrophile? So is this arrow reasonable?
No, oxygen already has a complete octet.
Excellent. So this wouldn't work. How about this? Can we have the oxygen be the electrophile here? Would this work?
No, because then the positive charge is in the middle of the chain of arrows.
Excellent. That's good that you're applying that rule. So that wouldn't work either. Any ideas then what would be a reasonable set of arrows based on the rules that we talked about previously? Who should go at the head of this arrow?
Carbon number 3, and then the bond which binds carbon 3 and oxygen could break, leaving the electron pair on oxygen. That would neutralize oxygen.
Excellent. Very good. So what role then is the iodine playing?
Nucleophile.
What role is carbon 3 playing?
Electrophile.
And what role is the oxygen playing?
Leaving group.
So we've discovered a surprising rule. When an atom has a positive charge, what role does it usually play? So in this case, who would be the electrophile?
In this case?
Following this pattern. If we follow this pattern we've just seen, here's who would be the electrophile.
Z.
Good, not Y. Do you see how that is pretty surprising? You might suppose that an atom with a positive charge should be an electrophile, but we've seen that usually doesn't work because that breaks the octet rule. Atoms with positive charges usually cannot be electrophiles because that usually ends up breaking the octet rule. Actually, when an atom has a positive charge, it's usually the attached atom that will be the electrophile. So this is a rule that most students don't ever quite internalize, but it comes up a lot in organic chemistry. It's the atom that's attached to the atom with the positive charge that will be the electrophile. And we just proved why that has to be in order for our arrows to be consistent with the rules we talked about earlier. So what role does the atom with the positive charge play?
Leaving group.
That's right, not electrophile. So the arrows would look like this.
Yeah.
So here's our general pattern. Notice, obviously, Y and Z are not real elements, right? I'm just using these as like placeholders to stand for any elements.
Yeah.
Okay, so that we can see the general rule. But here's an example. This is an example of the rule we were just talking about down here with actual real elements. And this rule we kind of just proved or explained. We explained why this atom can't. We explained why this can't be the electrophile because that would usually break the octet rule, or end up putting a positive charge in the middle of the string of arrows. So this is the only way to make that work. Okay. That's a very important rule. So try this problem on your screen. Try putting in some reasonable electron pushing arrows.
Okay. Okay.
Okay, great. So the most common mistake people would make, so describe the roles that atoms are playing here.
Here, bromine would be the nucleophile.
Why is that reasonable?
It has a lone pair, negative charge.
Because it has a negative charge. Just a lone pair would not make it a great nucleophile, but the negative charge makes it a nucleophile. Good.
Okay. And carbon-2 would be the electrophile. It's
good. And what role is the oxygen playing?
The leaving group.
Good. Now, something we're going to have to do from now on is we always have to describe why the roles are reasonable. And I'm going to kind of tell you what I think is the best way to describe those, and then we'll just keep practicing them over and over. So
okay.
Why is carbon-2 a reasonable electrophile? Because it's attached to an atom with a positive charge.
Okay.
Why is carbon-2 a reasonable electrophile? Because it's attached to an atom with a positive charge. That's the best way to describe it, and we'll just keep practicing that because that's such an important rule. And why is the oxygen a good leaving group? Because it has a positive formal charge. We've seen that when you have a positive formal charge, that makes you a leaving group, and it makes the attached atom the electrophile, usually. So why is carbon-2 a reasonable electrophile?
Because it's attached to an atom with a positive charge.
That's right. And why is the oxygen a good leaving group?
Because it has a positive charge.
That's right. And why is the bromine a good nucleophile?
It has a negative charge.
Okay, great. All right, excellent. So this is a reaction you did see in the first semester, but even if you didn't remember this, you could still figure it out now. Now we started to make some good progress. We've started to go over enough rules that you can actually predict all the arrows sometimes. You predicted every single arrow here. That was very good. I'll go back to my screen. This is not necessarily an easy problem. The thing that's tempting to do is this. This is tempting, but this is incorrect, because this would make the oxygen the electrophile. But usually the atom with the positive charge is not the electrophile. Usually it's the attached atom that's the electrophile. Very good. All right, see if you can predict one of the roles that an atom will play here.
Well,
using the rules we've talked about so far.
Either carbon-1 or carbon-2 would make a good electrophile.
So should it go at the head or the tail of an arrow?
The head.
Okay, good. Could this be the only arrow?
No.
So
there could be another.
So what's another role that an atom has to play here?
Well, that bond between carbon-2 and oxygen would break making oxygen a leaving group.
So that's right. The oxygen has to be the leaving group here. Good.
Yeah.
Why is carbon-2 a reasonable electrophile?
It's next to an atom with a positive charge.
Good. It's attached to an atom with a positive charge. Good. And why would the oxygen be a reasonable leaving group?
It has a positive charge.
Excellent. Now, we haven't gone over the rules to figure out who the nucleophile would be here yet, although you might have a good guess, so we'll just draw those arrows. So what's the most common mistake? The most common mistake is to think that the oxygen will be the electrophile. But that's not consistent with what we said.
Yeah.
Good. All right, let's see. This is a little tricky, but can you identify what might be a reasonable role for one of these atoms to play?
Well, because iron is a metal with a negative charge, one of the bromines attached to it could make a good a good nucleophile.
Good. That's a reasonable supposition. That's reasonable. That turns out not to be what happens here, although that does seem reasonable. Let's think about it another way. What's another role that a different atom could play here? And so think about, so what you just said seemed reasonable. It's not what really happens, but it was a good idea. Let's try something else, though. What's another role that an atom could play here?
Well, if the first bromine listed on the left were to be an electrophile, then that positively charged bromine could then become a leaving group by receiving that electron pair from that bond.
Okay, excellent. And we haven't talked about who would be the nucleophile here. Now notice, okay, so this is what I was going for. So the most common mistake people make is a lot of people would assume that this bromine should be the electrophile because it has the positive charge. But we've seen that when an atom has a positive charge, it's usually the attached atom that's the electrophile. And the atom with the positive charge is the leaving group. By the way, notice that these arrows don't involve this negative charge. But do you remember we talked about earlier today, when there's two formal charges in the same molecule, you're usually not going to use both of them. When there's two formal charges in the same molecule, we're usually not going to use both of them. So this is consistent with that rule as well. So it turns out we're using the positive charge here. It would be hard to guess whether we were using the positive or the negative. So you started by trying to use the negative. That was a reasonable guess, but it turns out that this is what actually happens. Okay, so the key thing is, do positive charges make things into electrophiles?
No.
Not usually, no.
Things attached to it.
But that's one of the most common mistakes that people make. Okay, good. Now, oh, I didn't write down the rule. Okay, so time to, or did I? I thought I wrote that. Yeah, here's the rule. Okay. We saw that why do positive charges not make things into electrophiles? Because that would break the octet rule usually.
Yeah.
All right. However, again, for every rule, there's usually an exception. All right. So the main exception here is carbons with positive charges.
Yeah.
What role would the carbon with the positive charge play?
An electrophile.
That contradicts our earlier rule. Doesn't that break the octet rule?
Nope.
Why not?
It did not have a complete octet.
To start with. Good.
Yeah.
Does it need a leaving group?
No.
Because it doesn't have a complete octet to start with. Okay. Yeah. So now this is a pretty darn important exception. This comes up a lot, obviously. There's lots of carbocations in organic chemistry. So here the exception is just as important as the rule. These are both very important. In fact, this exception comes up very frequently, so it's not like it's unimportant. But you have to keep in mind that it's only when a carbon has a positive charge that it makes it into an electrophile. Otherwise, atoms with positive charges are leaving groups. So notice the important thing here is, what element is this?
Carbon.
Yeah. So this applies to carbons with positive charges. Okay. Whereas this is pretty much anything but a carbon.
Okay.
So let's try this problem on your screen.
Okay.
So in this case, try to put in a complete set of electron pushing arrows.
Okay.
Okay, great. Let's put in some numbers so we can talk about this more easily. So what roles are atoms playing here?
Okay, so the iodine with its negative charge plays the role of nucleophile, and carbon number 2 would play the role of electrophile.
Good. Why is the iodine a reasonable nucleophile?
Has a negative charge.
And why is carbon 2 a reasonable electrophile?
It's a carbocation.
Excellent, great. Now it's good that you didn't just say because it's a cation, because cations are not usually electrophiles. The important thing is that you said it's a carbocation, because only carbon cations act like electrophiles. Normally cations act like leaving groups. Okay, so even if this is a reaction you saw in the first semester, but even if you'd never seen it before, you could have worked this out using the rules we just talked about. We completely predicted the arrows there. Good, I'll go back to my screen. Let's try this example on your screen. Try to come up with a complete set of electron pushing arrows here.
Okay.
Great. So what are the roles that atoms are playing?
Iodine would be the nucleophile.
Why is that reasonable?
Has a negative charge.
Great. What's another role?
Carbon 2 would be the electrophile because it's attached to a positively charged atom.
Excellent. Perfect. That's a little complicated, but you said that, you expressed that well. Good. And what's another role?
And the oxygen would be the leaving group because it's a positively charged atom.
Excellent. All right. Perfect. Very good. Okay. So let's go back to my screen. So a lot of students don't realize the difference between these. Notice that in this example, the atom with the positive charge was the electrophile. But in this example, the atom with the positive charge was not the electrophile. So most students are not familiar with these rules, but now we've gone over this. It's because there's a difference between having a positive charge on a carbon and on anything else. Why do carbons behave differently than other things? Because unlike most other things, carbons with positive charges have incomplete octets. Does an oxygen with a positive charge have an incomplete octet?
No, it has a complete octet.
Yeah, even though it has a positive charge. How do you know? How could you possibly know that? Well, because we just memorized it. We just memorized that. Okay, good. We memorized that even atoms with positive charges usually have complete octets, except for carbons with positive charges. Okay, good. Excellent. So using the rules that we've talked about so far, what's a role that we could expect an atom to play here?
Carbon number 2 would make a good electrophile, and because it's attached to an atom with a positive charge, while oxygen would be a good leaving group because it has a positive charge.
Good. That's good. Excellent. Now I have to be a little bit careful. We talked about this issue before. Technically, this oxygen is not called a leaving group because it's not really leaving carbon 2.
Okay.
Technically, this is not called a leaving group, but I can see why you would say that. Remember, we called, maybe it's kind of like it's kind of similar to a leaving group. It's kind of a pseudo leaving group. It's technically not a leaving group, but it behaves very similarly to a leaving group. So you still figured out the correct pattern here. Maybe I should add this though to my list here. So another pattern here's another pattern. So who would be the electrophile here?
Z.
And we still need this arrow to make room so we don't break the octet on Z.
Yeah.
But now I'm not going to label Y as the leaving group. because it's not exactly a leaving group anymore. There isn't really a great name for what Y is doing. There isn't a great name for what Y is doing in this case, so I won't give it any name, but we still have to put in the arrow. So this is another pattern that follows, this is another example that follows that same pattern. Okay, so whether there's a sigma bond or a pi bond, you follow the same basic pattern, although we don't quite call this a leaving group anymore. It's in many ways similar to a leaving group. Okay, good. The important thing is you predicted the correct arrows. Now, we haven't gone over the rules yet that would tell us who would be the nucleophile here, although you might have a good guess, so for the time being, I'll leave that blank. Okay, so by the way, this is one of the most important types of reactions in the second semester. This comes up lots and lots in the second semester. Good. Let's see. Oh, rats. This example was not a great example. If you remember this example, I should have drawn this example like this, actually. Let's actually do this example again. I got that wrong the first time. Okay. So remember we said originally that what would happen here was this, if you remember this example. Now, actually, now that I think about it, this was incorrect, although it was consistent with what we talked about before. What would actually happen here is this, just this. What role is the oxygen playing here?
A leaving group?
That's right. The oxygen is playing the role of the leaving group. And there really isn't any name for what carbon-2 is doing. Remember, there's not really any particular name for the atom that loses the leaving group. Okay, so my point here is sometimes the leaving group can fall off without being pushed. Sometimes a leaving group can fall off without being pushed. How do you know? So how do you know when to follow this pattern and when to follow this pattern? Well, you just have to learn more organic chemistry. It depends on the details of the situation. So as you go through organic chemistry, you'll learn some details to decide which pattern you're going to be going through. So let's add that as another pattern.
Okay. And should there be two hydrogens attached to that oxygen?
Thank you.
Make that positive?
Thank you. That's correct.
Okay.
That's a good point. That's a good point. That's good that you noticed that. So here's another pattern. What role is atom Y playing here?
Leaving group.
Notice how is this different from the first pattern? Z is not playing the role of the electrophile here yet. We just have this playing the role of the leaving group. Okay, how do you know when you're going to follow this pattern and when you're going to follow this one? Well, you have to learn more organic chemistry. You have to learn more organic chemistry so you can figure out the difference between the various cases. You can kind of see what's happening here, though. Draw the product of this step on your screen.
Okay, looks like it would become and
Excellent. Good. So you changed two charges. Now we formed here a carbocation. Is this an acceptable carbocation?
yeah, it is a secondary carbocation.
We've talked about how those are acceptable. What types of carbocations are not allowed?
Primary.
That's right. Good. So going back to my screen, we can actually start to see why this, in this case, why this case was different. Why would this arrow not be reasonable? What type of carbocation would this form?
That looks like it would form a primary carbocation.
So you can kind of see that's the ochem we can use to distinguish between these two cases. The leaving group here can just fall off without being pushed because it forms a reasonable secondary carbocation. But this leaving group has to be pushed because otherwise it would form an unreasonable primary carbocation.
I see, yeah.
Okay, so that's, remember I said, how do you decide whether you're going to follow this pattern or this pattern? You have to use other ideas from OChem. So we just talked about one example of that, although there's other things that can come up as well. Okay, now we're not covering all the cases here. There's other situations here. So you just have to go, for each new reaction, you have to decide which pattern it's going to be. Also, I want to point out, remember we said earlier that you normally want to put a negative charge at the beginning of the arrows and a positive charge at the end.
Yeah.
But I did say that there's actually a fair number of exceptions to that. Notice this is actually an exception because we're not using this negative charge. That should have made you a little uncomfortable. Normally we want to use both the negative and the positive charge. But there are a fair number of exceptions to that rule. That rule has a fair number of exceptions. So you normally want to try to use both the negative and the positive charge in your reaction, but there are a fair number of exceptions to that, and this turns out to be one of those exceptions. In this case, the negative charge is not going to do anything in the first step of the reaction. It's going to wait around for the second step of the reaction. We may as well go back to your screen. So go ahead and draw again the sodium iodide. That's still there. So what you've drawn is the product from your first step. So why not go ahead now and try to draw? Actually, why don't we put this in your notes so it's correct. Go ahead and draw these starting materials so you have the full reaction in your notes. So to the left or up above, draw this set of starting materials. Good. So you just figured out what's going to happen in the second step. And you may as well draw the product from that too. Okay, good. All right, so the main point I wanted to make, let's scroll to the left again a little bit. We said earlier, go ahead and put in the charges on the sodium iodide in the first step, even though they're not participating. We said earlier that when possible, you should always use the charges in the reaction. Put the positive at the beginning and the negative at the end. But I did warn you that there are a fair number of exceptions to that. And here we're seeing an exception. In this case, the negative charge just waits in the first step. It doesn't do anything. It doesn't come in until the second step. You can kind of see why this is somewhat reasonable because it formed a secondary carbocation, which we know is possible. All right, so I'll go back to my screen. So basically, I don't know if you remember, but the difference between these two is this reaction here is an SN2 reaction, and this reaction that we did here was an SN1. It's something that you learned in the first semester, but now we've kind of gone over why these end up being different. But the point is, even if you've never heard those terms SN1 or SN2, you can kind of predict what might happen here, or at least see why these are reasonable. Okay, all right, so anyway, my point is, sometimes when there's a positive charge, the attached atom is the electrophile, and the atom with the positive charge is the leaving group. But sometimes when there's a positive charge, the leaving group just leaves, and the attached atom is not the electrophile until the next step. How do you know which pattern it's going to form? Well, it depends on the particular details of the particular reaction, so you'll have to learn how to tell the difference between those by studying more organic chemistry. That's something that you'll learn more about as you go on through the course. Okay. All right, so notice things are getting kind of complicated. I think right now you have a very good understanding of this, but notice how it would be very easy in a few days or weeks to start forgetting this, right? Notice how for negative charges there was a rule, but then there was an exception about metals or semimetals. And then for positive charges there was a rule, but the rule has 3 different cases, and then there was an exception to that too. So I think right now you have very good understanding of that, but you can see it would be very easy to start forgetting it. So it's important to take very careful notes on what we just talked about and review that continually, because the amount of material is now starting to pile up a little bit. By the way, I'll mention one other exception here that's pretty obvious. Obviously, what role would this play in a reaction?
Spectator.
Yeah, so that's another exception to this rule. We said here that atoms with positive charges are leaving groups. Well, not when they're metals. Metals with positive charges are just spectators.
And what about hydrogen?
A hydrogen with a positive charge?
Yeah.
That's a great example. That's an excellent question. That's a great example. Well, what do you think? Does it seem more like the rule or more like the exception?
It seems more like an exception.
How so?
It has an incomplete doublet.
Excellent. So that's great. That's really good that you thought about it that way. That's a very good extension. Great. So that's right. We said carbon can be an electrophile with a positive charge because it has an incomplete octet. But you remembered we said hydrogens with a positive charge have an incomplete doublet. So yeah, you might put this here. That's a great point. Also, it's pretty obvious because in this case, obviously the attached atom would not be the electrophile because there is no attached atom.
Yeah.
A hydrogen with a positive charge is just a bare proton. It doesn't have an attached atom. So the reason, though, I'm not going to do that is because technically this is not an electrophile. Technically, this is an acid.
Okay.
If you remember that term. This is a symbol for a strong acid. And that's a topic I want to go over later, actually after this topic. So after we finish going over nucleophiles, so what are the roles that we've discussed so far in organic chemistry? What are the roles in organic chemistry?
Nucleophile, electrophile, leaving group.
Good. But there's two more roles that we haven't talked about yet. The other two roles we haven't talked about yet are acid and base. And that's our next topic. After we finish going over the rules for nucleophiles, electrophiles, and leaving groups, the next thing to go over is acids and bases. That's very important in organic chemistry and even more important in the second semester than in the first semester. Okay, so technically I'm not going to go over this quite yet because it's probably better to think of this as an acid than to think of it as an electrophile. But you're right that it is quite similar. It really follows this pattern. It does follow this kind of exception pattern rather than the rule pattern. So that was a good point. That's good that you thought about that. That's good. Okay, in any case, to finish up this, metals with positive charges are just spectator ions. I think we already know that. So that's an exception that's pretty easy to remember. Okay, so do you have the handout on reactivity that I sent you?
Yeah, got it right.
Excellent. That's good that you still have that handy. Now, we've been mainly talking about the top of page 2, right? We've gone over the rules for using electron-pushing arrows at the top of page 2. I think we have a good understanding of that. Now let's move to the bottom of page 1.
Okay.
The bottom of page 1. Does this table look familiar?
Yeah.
So this is what we just talked about, right? This is a summary of what we've just been talking about. When an atom has a negative formal charge, what role does it usually play?
Nucleophile.
An atom with a negative charge is the nucleophile, like in this example. However, exception, if the negative charge is on a metal or a semi-metal, then the attached atom is the nucleophile, and it donates the electrons from its bonds. And here's the exception. When an atom has a positive formal charge, most atoms with positive formal charges play what role?
Leaving group.
Good. And it's usually the attached atom that's the electrophile. So here's this pattern. Although, all right, so here's that kind of pattern. Although we saw sometimes the leaving group can leave without being pushed. Here's an example where the leaving group leaves without being pushed. But there's an exception, which is when the positive charge is on a carbon. Then no leaving group is necessary. Also, I also mentioned there's also an exception when the positive charge is on a hydrogen. That's the example you're just bringing up. Then the hydrogen is an acidic proton. And we also talked about how metals with positive charges are unreactive spectator ions. All right, like I said, I think right now you have a very good understanding of this, but it would be very easy to start forgetting these ideas. That's the purpose of my giving you the handout. The handout gives you something that you can keep reviewing. The reason for this is you probably have quite a few notes now, and it's easy for the important ideas to get lost in students' notes after a couple weeks. So that's why I'm giving you this handout. The handout is summarizing the most important stuff we've talked about, so it won't get lost in your notes. So you can keep reviewing it. So it's important, don't just review your notes, although that's impossible. It's even more important to review the handout. So far, we've only talked about 2 parts of the handout. We've talked about these ideas from page 2, and we've talked about now this from page 1. Okay, very good. Okay. Well, actually, we've made some good progress here. So remember, what we're trying to do is we're learning how to draw electron-pushing arrows when they're not given for us, the most important skill in organic chemistry. And remember, most students think they're just supposed to memorize the arrows for every single reaction, but that's really impossible. There's too many reactions. You're supposed to be able to figure out what arrows might be reasonable. And what's the most important factor for figuring out the reasonable arrows?
The charges.
Charges. If you think about it, though, we've finished that. We've talked about how to interpret negative formal charges and positive formal charges. We've talked about the rules and the exceptions for using negative and positive formal charges to figure out the roles that things are going to play. Negative charges is pretty simple. What role do things with negative charges usually play?
Nucleophile.
Positive charges are more complicated. What role do atoms with positive charges usually play?
Leaving group.
Except for carbons, which play the role of
Electrophile.
But now, that's not enough. What if there is no negative formal charge? Who's going to be the nucleophile then? And what if there's no positive formal charge? Who's going to be the electrophile and leaving group then? So that's the next topic. That's the more challenging topic. What do you do now when you don't have a formal charge to figure out who's going to be the nucleophile or the electrophile? Well, let's start with leaving groups. So first of all, what's the best sign of a leaving group? What have we talked about so far is a good sign of a good leaving group?
A positive charge.
Right, a positive charge on a non-carbon.
Yeah.
Is a great sign of a leaving group. But what if nobody has a positive charge? So these are the rules for finding the leaving group. How do you identify the leaving group? First, look for an atom with a positive formal charge, like this. If no one has a positive formal charge, well, you tell me, do you remember what's a type of element that can be a leaving group that doesn't have with a neutral formal charge? So there's lots of elements in the periodic table: sodium, lithium, bromine, chlorine, nitrogen, oxygen, carbon, hydrogen, sulfur. Can you think of any examples of a neutral atom that's a good leaving group?
Maybe chlorine.
Yeah, that's right. If you so I don't remember how well you remember these reactions, but this is a normal SN2 reaction from the first semester. And what role is the chlorine playing?
A leaving group.
That's right. So anything else besides chlorine that can be neutral and a good leaving group?
Bromine.
Yeah, so basically neutral chlorine bromine and iodine are good leaving groups. They're actually very good leaving groups. Even though they don't have a positive charge. Okay, good. How about fluorine? Fluorine does not go in this list. That shouldn't surprise you. I don't know if you remember, but fluorine actually isn't used much in OChem. We rarely or never use fluorine in organic chemistry. Very rarely is fluorine used in organic chemistry, and it's not in this list. Fluorine is also a halogen, but it's not a great leaving group. Okay. Let's see if we can try to figure out why. By the way, any other neutral element is usually not a good leaving group.
Okay.
Although, again, there are some exceptions to that we'll talk about later. Most other neutral elements are not acceptable leaving groups. Except for some exceptions that we'll talk about in another session.
Okay.
But normally you should assume that neutral elements are not acceptable leaving groups unless you've specifically learned otherwise. You should assume that neutral elements are not acceptable leaving groups unless you've specifically learned otherwise. These are the only ones that we come up a lot that are good leaving groups. Okay. Let's try to see why that is. Try to do this example on your screen. Draw the product from this reaction.
Okay.
Okay, good. By the way, this is what's called an SN2 reaction, maybe the most important reaction in the first semester. I don't know if you remember that reaction. All right, so now what is the definition of a leaving group?
It is something that receives electrons to leave something.
Good. So if you start neutral and you receive electrons, what charge do you get?
Negative.
As you can see here. But things don't normally like being negative, right? That's why most neutral elements are not good leaving groups. Maybe I'll go back to my screen.
Uh-huh.
You can see why neutral elements are usually not acceptable leaving groups because they don't want to get a negative charge. Neutral elements are not acceptable leaving groups because they don't want a negative charge. Why are these elements better able to stabilize the negative charge than most elements could be? Can you think of anything that would make the chlorine better at stabilizing this negative charge than other elements?
Is it because it's very electronegative?
That's right. What does electronegative mean? Does it mean it wants electrons or doesn't want them?
Wants them.
I think that should make it obvious why that makes it a good leaving group, right? If you want electrons, you would want to, that would make it easier to be a leaving group because leaving groups take electrons. Okay, so all of these halogens are towards the right of the periodic table, so they tend to be relatively electronegative compared to the things to their left. Because these are to the right, they tend to be electronegative, which means they want electrons. So that can explain why these are pretty good leaving groups. There's another reason, though, that I think is more important that you might not have thought about. The more important reason is, if you're looking at your periodic table, most of the elements in organic chemistry, most of the elements from organic chemistry are from the second row of the periodic table, correct?
Yeah.
But these are not from the second row. What row is chlorine in?
The third.
And bromine and iodine are from the fourth and the fifth.
Yeah.
That means they're big. That's the most important reason why these are good leaving groups. The most important reason that they're good leaving groups is because they're big. How would being big help to stabilize this negative charge? Well, we've talked about this. Do you remember, do charges want to be concentrated or spread out?
Spread out.
Well, who can spread a charge out better? Something big or something small?
Big.
Because it's got more room. That's the most important reason that these are good leaving groups. The most important reason they're good leaving groups is because they're bigger than most other elements in OChem, because they're from the third row and below. Okay, so by the way, that's why fluorine is not a good leaving group. You might think that fluoride would be a great leaving group because it's the most electronegative element in the periodic table. But that's counteracted by the fact that it's so tiny that the negative charge can't spread out at all. Fluorine is also one of the smallest elements in the periodic table. So that's why it's not a good leaving group, even despite its electronegativity. Okay, I hope that made sense, but we should also pretty much just memorize this. We should just memorize that these neutral halogens are good leaving groups.
And is there a reason to know which is a better leaving group between those three? Or is it not that important?
That's a great question. That's great that you asked that. That's thinking like an organic chemist. That's good. When you ask that type of question, you're thinking like an organic chemist. So that's good that you were thinking about that. That's not going to be tested usually too much in the second semester of OChem, because that was a first semester topic, but it certainly could come up on the DAT. So we can briefly talk about that. Well, do you remember we said what's the most important factor that makes these good leaving groups?
They're big.
So you should be able to use that to figure out who's the best leaving group.
Okay. It would be iodine.
That's right. In fact, remember, why is fluoride not a good leaving group?
Because it's small.
That's right. So that was an excellent question, but we have the tools to figure that out. So of these, which is the worst leaving group?
The chlorine.
Right. Iodine and bromine are better leaving groups than chlorine. But usually chlorine is good enough to be considered part of the group. All right. But the most important thing is that you ask that question. That's important. It's important in organic chemistry not to just be blindly memorizing, but thinking critically and asking those types of questions. So that's good that you thought about that. And now we saw how we could evaluate that as well. Okay. So in general, if two elements are in the same column of the periodic table, who's the better leaving group?
The lower one.
Because it's
bigger.
That's right. Okay, good. We won't go into that too much right now, but that certainly is a topic that could come up on the DAT. It won't be too important in the second semester of your course, though. It's more of a first semester topic. All right, in any case, we also just want to memorize that these are good leaving groups. So now we have a good way to determine leaving groups. First, look for positive formal charges, and then look for halogens. There are a few other ways that neutral elements can be acceptable leaving groups, but we'll have to come back to those later.
Okay.
Right, let's try this on your screen. Try to draw in some reasonable electron pushing arrows. Excellent. So describe the roles.
The carbon 5 here would be the nucleophile. It's negative charge.
Because it's negative. Good.
Yeah. And carbon 2.
This is a little tricky. We haven't quite said why carbon 2 would be... What role is the carbon 2 playing?
Electrophile.
Right. Now, we haven't quite said why that's a reasonable electrophile, but it is an electrophile. And what role is the bromine playing?
The leaving group.
And why is that reasonable? Well, it's reasonable because we've memorized that bromine is a good leaving group. Remember, we need to keep just saying why things are good, why things are reasonable. So we can just say bromine is a good leaving group because we've memorized that it's a good leaving group. Okay, although we did explain that in more detail together. Okay, very good. Notice, though, that that is what happens here, although you might have considered this. Sometimes leaving groups just leave without being pushed.
True.
In this case, you are on the right track. This is what actually happens. How do you know which happens? Well, that would take more work. You'd have to study the particular reaction in more detail. So it's hard to tell which of these would happen. This is more common. It's usually more common to get pushed. So usually you should assume that the leaving group is going to get pushed unless you have some particular reason not to. So maybe I shouldn't even have mentioned that. I don't want to confuse you or overwhelm you too much. But it's good to keep in mind it's not quite as simple as this seemed. There are other possible patterns. But what you drew is what actually happens here. Okay, good. Does this molecule have any acceptable leaving groups?
Yeah, the chlorine.
Good. Does this molecule have any acceptable leaving groups?
Yeah, the oxygen. Great. With its attached carbon chain. I guess the oxygen itself would be considered the leaving group, right?
Right. Well, it's ambiguous. These roles can refer to either atoms or groups of atoms. So we could say the oxygen is the leaving group, or we could say oxygen 4, 5, 6 is the leaving group, or oxygen 3, 2, 1 could be a leaving group. So, but I think it's more useful for us right now to focus on atoms. So for us, we'll say that the oxygen is the leaving group. Okay, good. Does this molecule have any acceptable leaving groups?
It doesn't appear to.
No positive charge. That's very important. It's very important to know when there's no acceptable leaving group. Does this molecule have an acceptable leaving group?
No.
Because everything's neutral, but there's no neutral halogens.
Yeah.
Does this molecule have an acceptable leaving group?
No.
Does this have an acceptable leaving group?
No.
Does this have an acceptable leaving group?
Yeah.
Okay, so it's very important to know when there's no acceptable leaving group. We can't force something that's not going to work. So the only leaving groups we've talked about so far are these. Good. And later we'll talk about a few more examples. Okay, good. So that about covers it for leaving groups. I said there are more rules, but these are the most important rules. So what do you look for first in the leaving group?
A positive charge.
But what if no one has a positive formal charge?
A halogen.
Yeah, except for fluorine. Good. Oh, we'll just assume that because fluorine doesn't come up much, so we can just say halogens. Good. Okay. All right, good. So, how about nucleophiles? To identify a nucleophile, what have we said you look for first?
Negative charge.
Good. And we talked about the rule and the exception for that. Great. But what if nobody has a negative formal charge? What then? Well, can you remember anything else from your course? What else can make something a nucleophile besides a negative formal charge?
Seems like an alkene, or a pi bond.
That's true. Excellent. That's an excellent point. So you can look for alkenes, carbon-carbon pi bonds. So it could be an alkene or an alkyne, because they both have pi bonds.
Yeah.
Okay, that's an excellent point. Good, that's good that you remembered that. What else? There's something that comes up more often than that. There's actually many cases where there's no negative formal charge. So what do we usually use to identify a nucleophile if there's no negative formal charge?
Something that's stable with a positive charge.
That's actually not a bad guess. That's actually a good point. That's good that you thought about it that way. That's a very good way to think about it. That's a very good way to think about it. Good. You're using the tools we talked about. That's a great way to think about it. Unfortunately, I think it's a little bit hard to figure that out. So let's look at it a different way. If there's no negative formal charge, you look for an atom with a lone pair. Does that make any sense?
Sure, yeah.
Yeah, so you might actually remember having done that. Okay, so you look for a neutral atom with a lone pair. Why? Well, is a nucleophile going to be an atom with stable electrons or unstable electrons?
Is a nucleophile going to be an atom with... it seems like it would be unstable electrons.
That's why it wants to donate them.
Yeah.
That's right. Well, the most stable electrons are sigma bonds. The most stable electrons are sigma bonds. Unstable electrons are in lone pairs or pi bonds. That explains these two patterns.
Okay.
Pi bonds and lone pairs are less stable than sigma bonds. So if an atom has a lone pair or a pi bond, it's going to want to try to donate it to turn it into a sigma bond. Okay. So here's our examples. Good. As usual, there's a pesky exception. Neutral halogens are not nucleophiles, even though they have lone pairs.
Okay.
That's pretty obvious. I think most people have already internalized that. Okay, do you have this written down?
Yeah.
Okay, so try drawing the arrows for this reaction on your screen. Great, and let's describe what roles are the atoms playing. Let's put in some numbers so we can talk about that more clearly.
Okay, so the oxygen from its lone pair would be a nucleophile.
That's right. So why is the oxygen a reasonable nucleophile? Because it has a lone pair, as you were mentioning. Why is the oxygen a reasonable nucleophile?
Because it has a lone pair of electrons.
That's right. Great. And what role is the carbon-2 playing?
Carbon-2 would be the electrophile.
And why is that reasonable?
It's receiving electrons to join with a nucleophile.
Okay. Now, that's right. That's not actually quite what I mean, though, when I ask that question, why is it reasonable? What I'm going for is, how do you know it's going to be an electrophile?
Because it has an incomplete octet.
Yeah. Or we can just say, because it's a carbon with a positive charge. Good.
Okay.
When possible, we want to use the charges. So why is the oxygen a reasonable nucleophile? Because it has a lone pair. Why is carbon-2 a reasonable electrophile? Because it's a carbon with a positive charge. Excellent. Okay, good. So in this case, we were able to find the nucleophile even though nobody had a negative charge. Very good. I'll go back to my screen. All right, can you identify here who might be the nucleophilic atom?
The nitrogen, because it has a lone pair of electrons.
So what, go with the head or the tail of an arrow.
The tail.
And you can probably figure out who will be the electrophile, but I'll be picky. We haven't gone over the rule for that yet, so I just won't identify the electrophile yet. It's pretty obvious, though. By the way, chlorine has a lone pair, right?
It does.
But it's not the nucleophile, is it?
No.
Yeah, that's what I meant by this exception. Neutral halogens have lone pairs, but they're still not nucleophiles. You probably already kind of know that anyway. So neutral atoms with lone pairs are nucleophiles, but not neutral halogens. What role do neutral halogens play?
Leaving groups.
Yeah, neutral halogens are leaving groups, not nucleophiles. Maybe I'll write it that way. Actually, one thing we should do here is notice I didn't draw in the lone pair on the nitrogen. So you must just have had memorized that neutral nitrogen has a lone pair, which is good. So we need to know which atoms have lone pairs. We should probably take a step back and do that.
Okay.
Does this carbon have a lone pair?
No.
So neutral carbons don't have lone pairs, do they?
No.
On the other hand, does a neutral nitrogen have a lone pair?
Yeah.
Yeah, it has one lone pair, like we just saw. And does a neutral oxygen have a lone pair?
Yeah.
Yeah, like we just saw, like in water.
Yeah.
Fluorine has a lone pair, but actually I'm not going to write it down because remember the halogens are not going to be nucleophiles. So I should say neutral atoms with lone pairs that can be nucleophiles. So actually, it's pretty much just stuff from these two columns. These two columns of the periodic table are what we're talking about. So for example, does this have a lone pair?
Yeah.
Because it's in the same column as
Nitrogen.
And does this have a lone pair?
Yeah.
Because it's in the same column as
Oxygen.
Good. And again, we won't write down the halogens, even though they have lone pairs, because they're not nucleophiles. Notice it's actually tricky. Is this a nucleophile?
No.
Is this a nucleophile?
Yeah.
Yeah. So I'm not saying that halogens can't be nucleophiles. I'm saying neutral halogens are not nucleophiles.
I see.
Neutral halogens are leaving groups. Remember, what's the most important factor in organic chemistry?
The charges.
So there's a huge difference between a neutral chlorine and a charged chlorine.
Yeah.
We've seen that charged halogens, negative halogens certainly are nucleophiles, but negative halogens, neutral halogens are not. Okay?
Okay.
So, does this have a lone pair?
No.
Because it's not in these two columns.
Yeah.
Pretty much, so what we're talking about is elements from these two columns of the periodic table. Also, I guess I should say, there are some metals that have lone pairs, but metals don't usually participate much in reactions. So we're really talking here about a neutral non-metal with a lone pair. We're talking about a neutral non-metal with a lone pair. Oftentimes neutral metals might have a lone pair, but they're not going to be nucleophiles anyway. All right, everything has all these little pesky exceptions. Okay, but I think we get the general idea here. So let's see. Let's keep going. So can you identify who would be the nucleophile here?
The sulfur, because it has a lone pair of electrons.
So does it go at the head or the tail?
The tail.
And we haven't quite gone over the rule yet for figuring out the electrophile, so I'll leave that blank. So this is an interesting case. Sulfur doesn't come up very much in organic chemistry, but it does come up occasionally. If it does, you should be able to figure out what role it's likely to play based on what we've just been talking about.
Okay.
Try this example on your screen. Try to come up with some reasonable electron-pushing arrows here.
Okay.
Excellent. Very good. So what roles are atoms playing here?
The oxygen on the right is the nucleophile because it has a lone pair of electrons.
Good.
Carbon 2 would be the electrophile because it is receiving electrons while joining with the nucleophile.
Now, that's actually not the way that's right, but that's not the way that that's not the way that I'm hoping for us to talk about that. We need to. It is receiving electrons, but we need to say, how did you know it would be a reasonable electrophile in the first place?
Oh, because it is attached to an atom with a positive charge.
That's what I'm going for. Good. That's right. So notice we have to start putting all the rules together in the same problem. Good. Okay. Most students, so a lot of students would think that the oxygen should be the electrophile, the oxygen with the positive charge. But we saw that's not right. When an atom has a positive charge, it's usually the attached atom that's the electrophile. Good. And then the oxygen, remember, is kind of like a leaving group, although we don't call it a leaving group here, because it's not actually completely leaving. Yeah. But in any case, you came up with you know these arrows are reasonable because the positive charge is at the end of the chain of arrows. All right, well, this is good. Now, this is not a reaction you've ever seen before, I know. This is a reaction from the second semester of OChem. This is a very important reaction from the second semester of OChem. But even though we've never seen it before, we were able to figure out reasonable electron-pushing arrows using our rules. Obviously, when you later study this reaction in detail in second semester OChem, hopefully now it will be much easier to remember this reaction because in a way we won't even have to memorize it. It'll make good sense to us in the first place. Okay, so that's some good progress on that. And you drew in those arrows correctly. I'll go back to my screen.
Okay.
There's a subtle mistake I've made here. What's the subtle mistake? It may seem like a weird question, but you're not allowed to put the tail of an arrow directly on an atom.
Okay.
So you have to draw in this case, you have to draw the lone pair in.
I see what you're saying. Yeah.
Now, you did that. You actually did that on the last problem. So you didn't make that mistake, but I just wanted to warn you against that. There's no real reason for that. It's just like a convention that chemists have come up with. For some reason, they don't like it when you put the tail directly on the atom. So you have to draw in the lone pair.
Okay.
The oxygen has another lone pair that you don't have to draw in because it's not using it, but you have to draw this lone pair. By the way, notice you don't have to draw in the lone pair when there's a negative charge. So where are you allowed to put the tail? You're allowed to put the tail on a negative charge, like this. Or you're allowed to put the tail on a lone pair, like this. But there's just an arbitrary convention that you're not allowed to put the tail directly on an atom. Okay. You've been doing that correctly, but I just wanted to mention that. Okay, good. All right, this is a good example here. You got that right. Let's see. Try this example. Try to come up with some reasonable arrows here.
Okay.
Okay, excellent. Good. So what roles are atoms playing here?
Oxygen, with because it has a lone pair, would be the nucleophile.
Great.
There is no negative charge, so you'd go to the next
Great.
thing.
Excellent. Good point.
And carbon 5 is a carbocation, so that makes a good electrophile.
Excellent. Okay, very good. So that's great that you worked that out. Good. So that's a good use of our techniques. By the way, this is what's called an intramolecular reaction. Intramolecular. That means one part of the molecule is attacking another part of the same molecule. That oftentimes feels weird to students or gives them trouble, but you notice you can just use the same rules as before to identify the nucleophile and the electrophile, even though in this case they happen to be in the same molecule. So that's great that you worked that out. Good. I'll go back to my screen. Second. Okay, good. So to review, what's the best sign of a nucleophile?
A negative charge.
But what if nobody has a negative charge? What do you look for then?
A lone pair of electrons, or a pi bond, carbon-carbon pi bond.
Yeah, carbon-carbon pi bond. See if you can come up with some reasonable electron-pushing arrows here. Try that on your screen.
Okay.
Okay, great. So what roles would you describe here?
Well, either carbon 2 or carbon 3 would be the nucleophile.
That's right. It doesn't matter because they're symmetric with each other here. Good.
Yeah.
And how do you know that they're reasonable nucleophiles?
Because of the carbon-carbon pi bond.
Excellent. Good.
And this first bromine is attached to an atom with a positive charge, so it makes a good electrophile.
Great.
And then the bromine, with its attached atoms there, would be a good leaving group because it has a positive charge.
Excellent. Great. Well, I know this is a reaction that you haven't seen before, so it's great that you were able to figure this out. I mean, you haven't studied it in your course because it's a second semester reaction. This is a pretty complicated, weird, scary-looking reaction, so it's good that you were able to figure out something based on the principles we've talked about. Now, you might feel a little nervous because we're not using the negative charge. We're not using the negative charge here, but remember we talked about when there's two formal charges in the same molecule, you're usually only going to use one of them anyway. So that's what's happening here. There's two formal charges in the same molecule. In that case, we usually only use one of them. In this case, it turns out we're using the positive charge. That's kind of has to be memorized a little bit. So it might have been reasonable to try to use the negative charge, but that's not what actually happens here. Okay, very good. All right. So these are some important rules then here for identifying nucleophiles. Okay, so I think the next thing that we have to go over is what's the most important factor in organic chemistry?
The charges?
That's right. Now, there's two different ways of identifying charges. What you and I have gone over so far is the formal charge system. But there's a whole other way of identifying charges, which is called the delta charge system. Have you ever seen, for example, these little symbols?
Yeah.
Okay, so this stands for a delta charge. Delta means a partial charge. So how do we identify delta charges? So delta charges occur, so first of all, delta charges only occur in covalent bonds. Delta charges only occur in covalent bonds, and they occur when one element is more electronegative than the other element. Delta charges occur when one element is more electronegative than the other element. How can you tell who's more electronegative? Well, for organic chemistry, you can basically just say who's more electronegative, elements to the right or to the left in the periodic table.
To the right.
So for purposes of organic chemistry, in general chemistry, it's more complicated. But for OChem, we can just say elements to the right are more electronegative. Good. So, who wants electrons more, bromine or carbon?
Bromine.
So who's going to pull the electrons in the bond closer to itself, the bromine or the carbon?
Bromine.
So the electrons are not going to be shared equally, like this. Instead, they're going to be pulled closer to the bromine. So what delta charge would the bromine have?
Partial negative.
And how about the carbon?
Partial positive.
Good. Now, what's bigger, a delta negative charge or a negative formal charge?
Formal charge.
Because a formal charge really represents -1, whereas this is more like, I don't know, -1/3 or -1/2. It's a partial charge. It's like a fractional charge. So delta charges are less important than formal charges in organic chemistry, but if there are no formal charges, you have to move to plan B and look for the delta charges. Okay?
Okay.
So, can you identify some delta charges here?
Yeah, it looks like chlorine would be negative delta charge or partial negative, and carbon 2 would have a partial positive.
Good. How about between 3 and 4? Who wants electrons more, carbon 3 or carbon 4? Well, that's kind of a trick question. They're both carbons, so they're going to be equally sharing the electrons, right? So notice delta charges usually only occur between two different elements. They don't occur between two of the same element.
Okay.
Also, here's another complication. Remember I said, how do you tell who's more electronegative?
An element to the right of the periodic table.
Good. But there's one element that doesn't work for. It doesn't work for hydrogen.
Okay.
Hydrogen is very far to the left in the periodic table. However, everything else on the left is a metal, and hydrogen is a non-metal. So the periodic table is misleading about hydrogen's electronegativity. So you need to keep in mind the electronegativity of hydrogen is similar the electronegativity of carbon. Why do you have to memorize that? Because it's not obvious from the periodic table. The periodic table makes it seem like carbon is much more electronegative than hydrogen because it's further to the right, but the periodic table is misleading about hydrogen in that respect. So we just need to memorize hydrogen is similar to what element in electronegativity?
Carbon. So,
are the electrons in this bond going to be equally shared or unequally shared?
Equally.
So will there be delta charges?
No.
No, so there's generally no delta charges between hydrogen and carbon. That's one of the reasons why bond line notation leaves the hydrogens out when they're on carbons. One reason we leave out the hydrogens when they're attached to carbons is because there's no interesting charges. Remember, what's the interesting part of organic chemistry? The atoms with charges. So that's why we leave out the hydrogens when they're on carbons.
I see.
Any delta charges here?
Yeah, delta negative on bromine, delta positive on hydrogen.
Now, how did you know the hydrogen was less electronegative than the bromine? Hydrogen is similar to who in electronegativity?
Carbon.
Carbon, and carbon is to the left of bromine.
Yeah.
So the bromine is slightly more electronegative than hydrogen and carbon. It's not a very big difference at all, but this still helps us. It's still helpful to label these because they give the right answers in OChem. Okay, good. When we treat these as delta charges, even though they're actually pretty small. Let's see. Any delta charges here?
Yeah, it looks like oxygen would have a delta negative. Perhaps both carbons 1 and 2 would have delta positive.
That's right. Good point. That's right. That's a good way to put it. And there's no other delta charges on these carbons, but they're hydrogens.
Right.
Good. Any delta charges here?
Yeah, delta negative on the oxygen, delta positive on both the hydrogen and the carbon covalently bonded to the oxygen. Carbon 3.
That's good. That's good that you noticed the hydrogen too. That's right. Any delta charges here?
Yeah, I think that the magnesium bromide would have a delta positive. The carbon
Good.
3.
Now let's focus on a particular atom.
Okay, magnesium. Delta
What's its charge? Delta positive. Good.
Carbon 3, delta negative.
Excellent. Very good. How do you know that carbon wants electrons more than magnesium?
It's further to the right on the periodic table.
Great. Do you remember, what do we call this type of molecule?
Grignard.
We talked about this a bit in a previous session. Notice that you might be tempted to also put in a delta negative between the magnesium and the bromine. And maybe there is one, but remember that we talked about how the halogen in Grignard's is never of any importance. It doesn't do anything. So there's no point trying to figure out anything about the bond between the magnesium and the bromine. Remember, we talked about how Grignards actually have two legal ways of being drawn. It would also be legal to draw the Grignard like this.
Yeah.
So is this the ionic or the covalent picture?
Ionic.
In the ionic picture, we use formal charges.
Yeah.
In the covalent picture, we use delta charges.
Okay.
But notice that in either way, the charges are consistent.
Yeah.
Negative charge on the carbon, positive charge on the magnesium. So which of these is correct? Well, they're both acceptable. Instructors go back and forth between both of these. Okay, good.
Okay.
Just take out your reactivity handout again.
Okay.
So can you find this table at the bottom of page 2?
Yeah.
So you can see we just covered this. Oh, I forgot to mention this. You generally do not use delta charges when there's formal charges. I should have mentioned that. When there's formal charges, we don't bother with delta charges, because who's bigger, formal or delta charges?
Formal.
Yeah, so you don't usually assign delta charges in a molecule that has a formal charge. But if there's no formal charges, well, if there's two identical atoms, we've said there's no delta charge, right? And if a carbon's bonded to a hydrogen, there's no delta charge. And otherwise, there's pretty much always a delta charge. And in organic chemistry, you can just say the atom to the left is the delta positive and the atom to the right is delta negative. That doesn't always work in general chemistry, but for the examples in OChem, this rule will work. Okay. So this is in the handout as well, because I think this is fairly important. This is something that people often miss. Will the delta charges usually be labeled for you in the problem?
No.
No, it's your job to put them in. So students often don't do this. When is it important to put in the delta charges? When is it important to look for a delta positive? When there's no formal positive. If there's a formal positive charge, there's no point looking for a delta positive charge. But if there's no formal positive charge, it can be very helpful to look for the delta positive. Okay, good. So if something has a delta negative, what role do you think it would be likely to play?
Nucleophile.
So we can actually add that to our list, right, of things to look for nucleophiles. You can look for a neutral atom with a lone pair or a delta negative. Okay, this is actually not very important because generally these go together. Usually if it has a lone pair, it'll also have a delta negative. For example, we said this was a nucleophile because of the lone pair. We could also have said it was a nucleophile because of its delta negative. We said this was a nucleophile because of its lone pair, but we could also have said it was a nucleophile because of its delta negative. So actually, for the most part, this is not very important. Usually people focus more on the lone pairs than on the delta negatives because they usually go together.
Okay.
But can you identify any roles that an atom might play here?
Yeah, it looks like carbon 2 would make a good nucleophile because of its partial negative charge.
Good. How do you know it has a delta negative?
Because it is a Grignard reagent, the magnesium bromide. The magnesium itself has the partial positive charge.
How do you know?
Carbon is further to the right on the periodic table.
That's right. So we don't need to memorize the delta charges in a Grignard. We can figure them out. Good.
Okay.
So would carbon 2 go at the head or the tail of an electron-pushing arrow?
The tail.
Good. Now this is a little tricky. Where do you think carbon 2 is going to get the electrons from that it's donating?
The sigma bond between itself and magnesium.
That's right. Normally, where do nucleophiles normally get their electrons from?
A negative charge, lone pair?
From lone pairs, but neutral carbons don't have lone pairs. Okay, good. So this is how Grignards react.
Okay.
Grignards, what role do Grignards play in reaction?
Nucleophiles?
That's right. Who's the nucleophilic atom in the Grignard? The carbon connected to the magnesium.
Okay.
Is carbon 4 going to be the nucleophile here?
No.
No, carbon 2, because it's the one that's connected to the magnesium.
Yeah.
Okay. By the way, do you remember there's another acceptable way to draw a Grignard? You could also draw the Grignard as ionically bonded.
Yeah.
Well, and remember, instructors would accept either picture. So in this picture, how would you predict what's going to happen? What role might an atom play here?
Carbon 2 would still be the nucleophile, but the tail of the arrow would go directly on the negative charge.
Because carbons with negative charges have lone pairs. Good.
Yeah.
And why is carbon 2 a reasonable nucleophile here?
Because it has a negative charge.
A negative formal charge.
So
notice that in this picture, the carbon is a reasonable nucleophile because of the delta negative charge. In this picture, the carbon is a reasonable nucleophile because of the negative formal charge. So this is why instructors don't care which picture you use. They don't care which picture because they both give the same answer. Either way, carbon 2 will be the nucleophile. Carbon 2 and magnesium. Magnesium is not in the first column, but in the second column. So it's similar enough to carbon in electronegativity that the bond is somewhere between covalent and ionic. Remember, the magnesium is just going to be the spectator ion here because it's a metal with a positive charge. Okay, so this is actually the only case where it's really important to use the delta negative to find the nucleophile. Normally you can just look for a lone pair for a nucleophile. But for Grignards, the only way to understand why Grignards are nucleophiles, if you're looking at this picture, you can understand it using the delta negative approach. And Grignards are pretty important in both semesters of OChem. Okay, good. All right, so that was, that's how we identify a nucleophile. Good. So then, how do we identify a electrophile? So this is a little tricky. To find an electrophile, what's the first thing you look for?
Something that's attached to a positively charged atom or a carbocation.
I said it was tricky, but that was a good answer. Yes. So you don't just look for something with a positive charge. You look for an atom attached to an atom. Attached to a non-carbon with a positive charge, with a positive formal charge. Or a carbocation. Carbon with a positive charge. That was a very good answer. Good. But what if nobody has a positive formal charge? What do you look for then? Well, here's what we already kind of talked about this. You look for an atom with a delta positive. Delta negatives are not too important for nucleophiles because usually you can just look for a lone pair. But delta positives are quite useful in finding electrophiles. Delta positives are very useful at finding electrophiles. Okay, so let's try drawing the arrows here.
Okay. Okay.
Great. So what roles are the atoms playing?
The iodine is the nucleophile because it has a lone pair of electrons, negative charge. And carbon-3 would be the electrophile. And bromine.
Why is carbon-3 a reasonable electrophile?
Because it is... It's funny, the words just left my mind. It's attached to the leaving group right there. My mind just drew a blank. It has a partial positive charge, that's why.
That's right. Remember, that was the latest rule that we were going over.
Yeah.
Good.
Sorry.
That's okay. And then what role is the bromine playing?
The leaving group.
Notice you don't explain that with the delta negative. You don't explain why the bromine is a leaving group with the delta negative. We've just memorized that neutral bromines are leaving groups. Okay, so the key thing here was the delta positive charge. Okay, so you drew those charges in correctly. Good. I'll go back to my screen. So let's try to draw some arrows here. Excellent. Very good. So let's describe the roles that the atoms are playing.
Okay. So the nucleophile would be nitrogen with its lone pair. And the carbon number 2, because it has a partial positive charge, would make for a good electrophile.
Because of the delta positive. Great.
Yeah. And then iodine is the leaving group.
And we can just say, because we've memorized that iodine is a leaving group. Good.
Yeah.
Okay, good. Now, something I wanted to mention is, remember, how many charges do we change on every step of every mechanism?
How many charges? 2.
Formal charges or delta charges?
Formal charges.
So I just wanted to point out, you do not worry about changing the delta charges when you're drawing the product of a reaction. When we said we were changing charges, we said we were changing formal charges. After all, yeah, good. For example, what's the delta charge on this nitrogen?
Delta charge on the nitrogen would be partial negative?
Yeah, that's another reason why it's a nucleophile, right? You said it was the nucleophile because of the lone pair. That was perfectly good. You could also have said it's a nucleophile because it has a delta negative. Go ahead and draw in the delta negative here. You don't usually have to do that, but you could draw in the delta negative here.
Okay.
What's the formal charge on the nitrogen?
There is no formal charge on the nitrogen.
So which of those are we going to use when we're drawing the product? Go ahead and draw the product here. Draw the product of this reaction.
Okay.
So what formal charge? So you said it became positive because what charge did the nitrogen start with?
No charge.
Right. But notice, sometimes students get confused and they think it started with a negative charge using the delta system. And then it would seem like it ended up neutral. So I just wanted to point out that that's a mistake people make sometimes when they're drawing in the delta charges. So it can be good to draw in the delta charges to predict the arrows, but the delta charges are not the charges that change in the reaction. The arrows tell us how we're changing the formal charges, not how we're changing the delta charges. In this case, there wasn't really much need to draw in the delta negative on the nitrogen because we knew it was a nucleophile from the lone pair anyway. All right, I hope that made sense anyway. I just wanted to warn you that the arrows change the formal charges, not the delta charges. We have those two different systems. Okay, let's go back to my screen. Let's draw some arrows here.
Okay.
Okay, great. This is another intramolecular reaction. So let's describe the roles that the atoms are playing.
Okay. Oxygen has a negative formal charge. That is the nucleophile. Carbon 1 has a partial positive charge, and it is the electrophile.
Because of that delta positive. Good.
Yeah. And bromine is one of the memorized good leaving groups.
Very good. That's exactly right. Excellent.
Yeah.
Good. I'll go back to my screen. Try drawing reasonable arrows here.
Oops.
Okay. Good. Now, one tricky thing here, we're not allowed to put tails on delta negatives. Where is carbon-6 getting the electrons from that it's donating?
Thanks. Yeah.
From the bond. You could put the negative charge on a full negative charge, on a formal negative, but it's just a convention. You don't put it on the delta negative. Okay, so what are the roles that the atoms are playing here?
The roles that the atoms are playing, carbon-6 would be the nucleophile. It has a partial or a delta negative.
Good.
And carbon-2 would be the electrophile. It has a delta positive charge.
Excellent.
The oxygen would be the pseudo-leaving group.
Is it a real leaving group?
It is not.
No. Now this is important. Are neutral oxygens acceptable leaving groups? Are neutral oxygens acceptable leaving groups?
No. They'd have to be positive.
They'd have to be positive to be an acceptable leaving group. The only neutral elements that are usually acceptable leaving groups are who?
The 3 halogens, the chlorine,
That's right.
bromine, iodine.
However, this reaction is still okay because the oxygen is just a pseudo leaving group, not a real leaving group. That's why we had to be kind of careful with our terminology here. A neutral oxygen is generally not allowed to be a regular leaving group, but this reaction is acceptable, and you can rationalize that because the oxygen is not a true leaving group. So this reaction actually is acceptable. This is actually quite important. Do you know what you call a carbon double bonded to an oxygen? What do you call it when a carbon is double bonded to an oxygen? That's called a carbonyl. Have you heard of that before?
Yeah.
Carbonyls turn out to be really important in the second semester of OChem. So this is a very important reaction. So carbonyls are, what role do carbonyls play in reactions? What role does the carbonyl carbon play in reactions?
Like in this case, it would be the electrophile.
And that's pretty much always going to happen. Because why are carbonyl carbons reasonable electrophiles?
They have a partial positive.
Yeah. Carbonyls are just about one of the most important topics in the second semester. Most of the semester is about carbonyl containing compounds. And what role do carbonyl carbons play in reactions?
The electrophile?
Because they're delta positive. And that turns out to work because the oxygen is not really, this is acceptable because the oxygen is not a real leaving group in this case. It's kind of a pseudo leaving group. Okay, so what you wrote down was good. You wrote down a correct, reasonable reaction. Good.
Could I ask one question on that?
Sure.
If that oxygen did not have a pi bond, I was wondering if there was a single bond with that oxygen and we had the same setup with the Grignard reagent. This would still be, this would still be a delta positive, as would the other carbon here, carbon 6. But it is not a carbonyl, and so does that mean that the it would not likely be the electrophile?
Even though it has a delta positive. That's right.
Yeah.
Yeah, that's an excellent question. A very, very good question. It's good that you're thinking about that. So why can't carbon 2 be the electrophile? It does have a delta positive.
Well, oxygen is neutral, and it does not make a good leaving group.
That's very important. Yes, that's an excellent question. That's very important in organic chemistry. That's right. So normally an electrophile has to have not just a delta positive, but also an acceptable leaving group. That's right.
Okay.
Normally an electrophile has to have both a delta positive and an acceptable leaving group. Carbonyls are an exception. The carbonyl doesn't really need a leaving group because it has this kind of pseudo leaving group situation. But a single bonded carbon has to have an acceptable leaving group. That's an excellent point. So yes, the Grignard would not attack carbon 2 in your bottom example. That's a very good point. The Grignard would not attack carbon 2. And that's very good that you're trying to think about similar but different examples. Again, that's thinking like an organic chemist rather than just trying to memorize things. So that was a very good point, and what you said was correct. Very good. Okay, that's right. Okay, so I'll go back to my screen. Let's see. So let's try to draw electron pushing arrows here.
Okay. Not sure. My first guess would be that would have had it there. Since this is not a good leaving group, I don't think that would happen.
Okay, excellent. Very good. Good. So this was a mean question, but you handled that correctly. The answer here is no reaction. Okay. You were getting pretty close to that. You didn't quite have the courage of your convictions, but you're getting pretty close to that. So that's good. There's no law of the universe that says that something always has to happen just because you mix two things in a beaker, right? Just because you put two things in a beaker doesn't mean something has to happen. Sometimes they just sit there and do nothing. So there would be no reaction here. It's important to know when there's no reaction. Sometimes instructors test that directly, but even if they're not testing it directly, it's still important for our understanding to know when there's no reaction. So what's missing here? What's the role that's missing? A good leaving group. So that's one of the most important skills in organic chemistry, knowing when you don't have a good leaving group. So by the way, what would be the next question an organic chemist would ask themselves? An organic chemist put these things in the beaker, nothing happened, they would be frustrated. The next thing they would ask themselves is, what can I do to give one of these a better leaving group? That's something we'll be studying later. The next thing you do, and you focus more on this in the second semester of OChem, an organic chemist is not just going to declare defeat, accept defeat here and say, well, I guess there's nothing I can do, I'll just close up the lab and go home. An organic chemist is going to try to change these reagents by adding other reagents to give one of them a better leaving group. And we're going to learn pretty soon, maybe in our next session, what you could do to start changing these to make them a better leaving group. And by changing, I don't mean using your pencil to change them. I mean what you could actually do in the lab to change one of these reagents. So we'll get into that later. So it's important to know when there's no acceptable leaving group. So that's good. So yeah, in this example, the answer was no reaction, even with the delta positive. Okay, so let's go back to my screen. So let's take a look at the first page of the handout. You can see, I think basically now we've covered the whole first page of the handout. So we made some progress here. When you're looking for nucleophiles, the first thing you look for in a nucleophile is something that, notice first here, this summarizes the definitions. A nucleophile donates electrons to join an electrophile. An electrophile receives an electrons to join a nucleophile, and a leaving group receives electrons to leave something. So, for a nucleophile, first you look for a negative formal charge. Otherwise, you look for delta negative or a lone pair or a carbon-carbon pi bond. So this summarizes ideas we've already talked about. For electrophiles, first you look for a positive formal charge. I could have been more specific and said you look for a positive formal charge for an atom that's attached. Usually you look for an atom that's attached to an atom with a positive formal charge or a carbocation. Otherwise, you look for a delta positive. And then for leaving groups, again, you look for an atom with a positive formal charge, and otherwise you look for these neutral halogens. Okay, now you might notice there's a couple ideas here we haven't quite talked about yet, though we've talked about most of these. Also, so what's the next thing for us to do? So we've made some pretty good progress here. We've covered some really important ideas, and we're starting to get to the point where we can predict what will happen in reactions we've never seen before, which is a huge advantage in organic chemistry, because then we don't just have to memorize every reaction, but it makes it easier to remember the reactions or to figure them out if we've forgotten them. So the next thing we have to do, I think we made some good progress here, the next thing is that there's two more roles, acids and bases. So the next thing we have to do is how to predict acid-base reactions. Acid-base chemistry is involved in almost every reaction. That's kind of the next important topic for us to get into, and those obviously acids and bases will be important on the DAT as well. So remember, the reason I gave you this handout is so that these ideas will not get lost in your notes and so that you have something to memorize. So this whole first page here needs to be memorized, except for the couple of things we haven't talked about yet. So you should work on memorizing the whole first page of this handout, except for a couple of things here we haven't talked about yet. You should already have the top half of the page 2 memorized. How to draw products based on electron-pushing arrows. This middle table we haven't talked about yet, but we might get to this soon with acids and bases. And now we've talked about this table at the bottom of page 2 as well. So you should study this and have this memorized as well, how to assign delta charges. So it's important to keep reviewing this. So I'll give you a warning. I think we're doing quite well here. I think you're making, you have a really good understanding of these ideas, but we've actually gone over a lot of material already, and it would be easy in a couple of weeks to have forgotten these ideas or to get them confused with other ideas. So it requires constant, continual review to make sure that these ideas are not getting confused, because I think we made a lot of good progress and we don't want to start losing that progress. But where we are now, I think we're in pretty good shape. So now would be a good time, like I said, to carefully review. We've actually gone over lots and lots of rules. And again, organic chemistry is challenging because almost every rule has all these pesky exceptions. So you've actually covered lots of material. And it's important to keep reviewing that, and so that the material is very clear in your mind, because what am I going to do on Thursday is dump a whole other bucket of rules on you for acids and bases, right? Every single session we're dumping a great new bucket of rules and exceptions, and it's easy for them to start to get confused. So it's important for you to keep reviewing those. But I think so far we've been doing good with that.